Hi, everyone. My name is Richard. I'm going to be talking about Tune, which is a distributed hyperparameter tuning library on top of Ray. So Tune is a joint work of many faculty members, graduate students, and undergraduates in the RISE lab. And here's just a couple profile pictures of many of the people amongst many others that are involved. And Tune sits here on the RISE stack on top of Ray, and is at the same level with RLib and Modin. And just for reference, the slides are already posted on the Slack channel. So if you are trying to take pictures, you can just read from the slides or use the slides for reference and sharing with other people in your organization. And so I want to start off with some motivation for like what is hyperparameter tuning, or like why hyperparameter tuning. So to give some motivation, we must all know about convolutional neural networks. These are very powerful machine learning techniques and are attributed to many of the recent advances in computer vision. However, one thing that gets less attention is the amount of time and effort spent on designing these networks. Here we have on the screen one of the original designs of a convolutional neural network by Kun. And after 20 years of research, the basic idea of convolutional neural networks hasn't changed much. But what has changed over the last 20 years is, first of all, the increased availability of compute resources. And also, you've mainly just changed like the shape of the neural network and the size of each layer. And this makes a huge difference in performance. Now, these are the knobs that we're calling hyperparameters. And so why do we care about hyperparameters? Why do we need actually a system? Why are we having a session in this talk to talk about hyperparameters? Well, so as a trainer of machine learning models, or if you're a model developer, you want the best model, right? But the thing is, to get to state-of-the-art levels of performance, training the model actually requires a lot of compute resources, and these compute resources are expensive. And even if you had a lot of money, you just simply can't buy time. And the time it takes to train a model to the state of the art can take days, if not weeks, to finish. So Tune is a system that aims to accelerate this process, specifically in the context of hyperparameter tuning, where you're training multiple models, multiple replicas of the same model over and over again. And Tune aims to provide model training to efficiently utilize the resources that you have available with minimal time and price. And so Tune, what is Tune? Tune is a hyperparameter tuning tool that is built with deep learning as a priority. This means that Tune allows you to utilize heterogeneous resources across your cluster. Tune allows you to tune your models with any machine learning framework. And finally, Tune allows you to do hyperparameter tuning across at any scale. So this is running from one single process to multiple processes or multiple GPUs on one node to running across multiple nodes, all without changing your code. And finally, Tune is also, just to comment on the popularity of Tune is integrated into many open source projects now, including AllenTune, which is an open source tuning solution from Allen Institute in Seattle, and also other research labs such as Liaw, which is Sergey Levine's group here at Berkeley. They also build libraries that depend on Tune. So here's a quick API walkthrough and kind of just to mention what are the features that Tune provides. So we start off here with an example training function. This is just an abstract convolutional neural network that takes in the configuration of hyperparameters and iterates through data in order to do training. And in order to integrate Tune into this training loop, all we need to do is track the loss, and we can use Tune's logging API to do this. And this is very, very natural, and it's very, it doesn't invade your code in any ways whatsoever. Now, to execute your training, you can do so typically as you would with a standard Python function. But if you want to do a hyperparameter tuning search, the first thing you would do is just change the command to tune.run. And if you want to scale out your search, you can add an argument here, and this allows you to run, what we've done here is we've run 100 training jobs, and the parallelism is set at the number of cores in your cluster. And Tune can also log your results automatically in various formats, including CSV, JSONs, and TensorBoard. And you can also automatically upload your training results to S3. This is a lot of like code that you typically might write around your training utilities, but Tune takes care of all this for you so that you can just focus on doing your research. And Tune finally also provides a lot of other features through this very simple API, including checkpoint restoring, designating a search space, as we talked about before, and choosing state-of-the-art search algorithms. So in terms of algorithms, Tune provides many algorithms that allows you to optimize your hyperparameter search. This includes state-of-the-art algorithms that Google uses, such as population-based training, or even open source libraries such as Axe from Facebook, or SIGOPT, which is an external connector to the SIGOPT service. So since the last retreat, we've added BOHP, which is a state-of-the-art hyperparameter tuning algorithm that jointly optimizes early stopping and Bayesian optimization in your learning process. We've also added warm starting support for many search algorithms, allowing you to optimize across multiple hyperparameter sweeps. This allows you to accelerate your hyperparameter tuning over and over again, and make sure that you use the previous results to your advantage. Another nice feature that we've integrated since the last retreat is native integration with TensorBoard hyperparameter tuning visualization. And so this allows you to look over all existing trials without modifying any of your existing code to support TensorFlow 2.0 or anything like that. And we're gonna have a section of this in the tutorial where you get to try this out. Another major feature I'd like to talk about for Tune is the integration with Ray's experimental distributed training model training APIs. So this is again experimental, but I think it's a really nice feature, and it's actually broadly used, or it's being slowly adopted in various research groups here. So let me give some background for why this is so exciting to me. Well, the first thing is models are becoming large and hard to train, obviously, and so we have here like a skeleton of a training script that fine-tunes an existing large language model. So you'll start with the model, but perhaps the model is too slow to train. So naturally, you want to use data parallel training. So data parallel training is actually not so hard to do anymore because there's a lot of framework support for this. Now, that being said, things do get a little bit more annoying once you want to start scaling out, adding multiple, doing like distributed data parallel training, where you would have to actually SSH into every single node and run these scripts. Now you might think like this might not be so hard. I can just write a simple script to sort of like take care of this for me. But the thing is, like, when you do training, you don't only want to run one single model. When you do model development, you actually, like, if you try to modify your thing to do anything new, your new idea often requires parameter tuning. And if you're in this situation where every single trial is a distributed training run, things become exponentially harder. So managing all these experiments is incredibly tedious, and trying to train multiple hyperparameters on these distributed jobs themselves at once will require a lot of organization, a lot of patience. And if a job dies or fails, you would have to be like logging into tens of machines in order to find out what exactly happened. So what does Tune provide you? So Tune provides a very simple integration with the Ray distributed training library that allows you to do a parallel distributed hyperparameter search where each trial itself is distributed itself. And you can do this with a very simple API, and also supports TensorFlow 2.0 and PyTorch. Now again, this is an experimental feature, so if you do end up trying this out in your organization, please get in touch with us, and we'd like to make it work for you. And if you run into any issues, please let us know also. Finally, I want to talk really quickly about some research that we've been doing on top of Tune, which we've used Tune to explore the problem of deadline-aware hyperparameter tuning. And so what this means is that if you're given the deadline of time t, and you're given some number of GPUs, you want to actually find the top performing, so the top trained trial at the end of the resource allocation. And so what we do is we use dynamic resource allocation, where we allocate more GPUs to more promising trials using Ray's experimental distributed training API, allowing us to beat existing solutions in a variety of benchmarks and models. And we'll be releasing source code and the paper about this soon, and so you should stay tuned. This will be appearing in a month at SOCC 2019. Okay, so that's it for Tune, and we should move on to the tutorials. Here's the link to the tutorials. You should be clicking the 3 notebooks on the bottom. And the trick here is that you have to uncomment the first cells in order to run on Colab. If you don't uncomment if you want to run locally, you can also leave the first cells uncommented. So don't touch that thing. And maybe in 15 or 20 minutes, we can walk through the first notebook together, just so that everyone sort of understands and can ask questions. I've already done the installation things, and so I'm just going to step through these cells and quickly talk about what we're doing here. And so I've imported some packages, and here's just a nice representation of your data. It's 4-dimensional, so we have the x, y of both of these two particular data points, or sorry, each data point has 4 dimensions, and x, y are all 4 of the dimensions. And what we want to do first is we want to have this model training, this model creation function, and we have this example training function that is typically done with Keras without Tune. And I think the point here is to show that comparing the standard training function versus the Tune training function is actually it's very similar. And in fact, the only thing that we're doing is we're creating this callback, which is called on each epoch of the training. And there's a total of 20 epochs, so this thing will be called 20 times. And so this is during the node training, so this allows us to plot the training curve later on. And so in order to make this function tunable, so to speak, you want to be able to have it pass in the configuration dictionary, which is given by Tune in generation if you're doing, say, random search, grid search, or even Bayesian optimization. So after we take this configuration dictionary, we want to be able to pass it into our model creation function. So what we're going to do here is just copy and paste this thing. And notice that the rest of the code remains the same. And I think the only big change here is that the callback has a Tune reporter callback. And so this should pass all the tests, and looks like it is very successful. So the next thing is we have this hyperparameter tuning space. Now the key thing here is that this is a Tune-specific helper function, and it basically just wraps a NumPy generation, NumPy random utility. And the only thing we're doing here is random search, so you shouldn't expect any of the configurations to depend on each other. Exercise 2 does have a Bayesian optimization exercise, so if you're interested in seeing how your trials can improve over time, that's probably what you want to look at. But for the sake of for a lot of problems, random search works actually very well, and Tune is here to help you execute your random training function. So we'll take this and we'll just copy and paste this, and then we want to increase the number of samples. This allows us to evaluate multiple training runs at the same time. And there were some questions about this shutdown and init function. The only thing this is doing is just clearing out the state in case you run into some weird issue. It's defensive, and you probably don't need to do this in practice. And actually, the only case where this is actually really useful is like in notebooks. So, and same with like this remove RF thing. It's like if you're playing around with things, I didn't want people to clutter up their tensor board, which you will see later on. So these things are all just defensive things. So I'm passing in the exact tuning function from above, right? Tune iris is right here, takes in the config. I pass in the tune iris function to tune.run. I set the verbosity to 1, and I have this hyperparameter space which was defined in the to-do. So I'm gonna run this right now. What we'll see is Ray will start, so this launches a mini Ray cluster internally on this collab machine. And you'll see there's like some output of the training logs. And slowly over time, you'll see that right here, there's like a number of resources requested. This is kind of abstracted away from the user, but mainly this says that each of my training trials is running 1 CPU, and I have a total of 2 CPUs on this machine, so I can run 2 in parallel. And we can see slowly this training is executing, and 2 things are running at the same time at all times. And so after a couple of minutes, we'll have all these things terminated, and we'll be able to not only compare the tuned model versus the original model, but also we'll be able to visualize the results on TensorBoard using TensorBoard's hyperparameter visualization tools. So this is gonna take maybe like another 5 minutes. But let's see what else is interesting here. Yeah, I mean, let's just wait until this thing runs, I guess. So actually, I guess another point to make here is that like on Collab, you'll see this thing get refreshed over and over again, and like it clears the screen. This actually looks a lot nicer on Jupyter Notebook, and it would have been nice if we could do that, but such is life. So this is almost done. All right, so we're done. So all these things are terminated, and we now have this analysis object that we got from the running. And so what we'll do first is we'll plot the data again. This is the test data, so it's a bit more sparse, and again, it has similar distribution as the training data. And we'll take the analysis object to obtain the log directory where the best trial is saved, and we're defining the best trial by the one that has the minimum validation loss during training. And we're going to take this best loss, and we're going to then evaluate it on the test data. And we'll see that in comparison to the untuned model, we have a 50% increase in accuracy. And so roughly, this is kind of like what the data distribution looks like in terms of the classification given by the tuned model. And we can compare what are the things that we got right and what we got wrong. And we can see there's some things that are kind of on the edge of the petal dimensions where the classifier wasn't able to classify correctly. Now, the funnest thing about this is this TensorBoard utility that basically was added in a month ago. So we'll see here that we have a bunch of training runs that are about to be visualized. In fact, it's like 20 specifically. And you can visualize all of these things at once. It's not clear why they're not showing right now, but, well, there we go. So you can see there's a couple training runs. Some of them perform better in the beginning, some of them perform worse in the beginning, and then over time, things start to average out. And so in this example, Tune doesn't really utilize this information, but in the second tutorial notebook, we do use this information, the intermediate training runs, for mechanisms such as early stopping, so killing unpromising trials, or even using doing Bayesian optimization, helping inform future hyperparameter selections using previously run trials. And so the other thing that I want to show here is if you click this Params utility, you can then wait for this to get populated, and you'll see all these things listed out, along with all the metrics that Ray that tune automatically visualizes or automatically logs. And so if we wanted to say, see which of the hyperparameters matters the most, we can take a look at this this view, which is this like scatter plot, or sorry, not a scatter plot, which is this parallel coordinate view. Now, what we really care about is so how do we read this? This tells us each line represents a hyperparameter configuration evaluation. So what this means is at the dense, so we have like a trial that has a high dense value, a dense 1 value, a low dense 2 value, so this first one, low dense 2 value, and a low learning rate. And we see that the validation loss is quite low. But like we can actually visualize this even closer, and we want to find exactly which one gave us the lowest validation loss. And we can see this one that had a high dense 2, a medium-sized learning rate, and a low dense 1 was able to get us a really well-performing trial. And so this is a very, very useful utility that Tune automatically integrates with for you to select your hyperparameters. And the nice thing, again, here is that you don't need to really do anything in order to get this to work. All right, so that's it for like the walkthrough of exercise 1. I think maybe we still have a little bit more time for you to do the rest of the exercises, and I'll be walking around to answer questions.